Gerd Danny, and he has done a remarkable job in putting this together. Now, I have a lot of ground to cover in an hour, and we'll probably take a break about 30 minutes in. Okay, let me go over my history in astronomy, and you can see it right in front of you. At age 12, I went to the Newark Museum, New Jersey, USA, to take my first courses in astronomy. At age 16, I attended a National Science Foundation school with a full fellowship for astronomer. At 16, I was granted an NSF scholarship to attend Mount Hermon School for summer to study all aspects of it as observational astronomy. In '67, I won the Missouri Academy Sciences top prize and was sent to New York City, where I worked with the amazing Carl Sagan. 1996, I created the first automated telescope in Cottage Grove, Oregon. My first emphasis was to find supernova in other galaxies. And I did this with a Celestron 14, a beta test Paramount mount. And I won't go into the details because I know everyone here is not, will not understand a lot of the technicals. In 1999, I moved to a dark site in Rio Rico, Arizona, and I created Tanagra Observatories Ltd. There I bought the land, built a house, and co-designed a 0.8 meter telescope and established Minor Planet Code 926. Notice from 1981 to 1997, I took some time off and I created and sold this company called Prime Factors, which still exists. And I essentially invented internet encryption. Let's continue on here. Hi. And let's go here. This is the web page I maintained when I was running Tanagra Observatories. This telescope is unique. There's only one of its kind on the planet. I co-designed it with a friend called Jim Ray. And if you notice, there is no place to put an eyepiece. Down here is an instrument bay. This is a 0.81 meter Ritchie Chrétien, which has a very large secondary here. Down in here is the instrument bay where I kept the CDC cameras and various other things. Then I added this telescope. This is obviously a Newtonian, and this is a very powerful CCD camera. Plus, there's a large piece of glass in there because Newtonians need correction. The one thing I should point out here is I've never used an autoguider. If you can permanently mount a telescope and really adjust it, autoguiders are not necessary. I should also mention that before I got the NASA grant, I sold time. I was the first one to sell time to a lot of universities, including Caltech, New Mexico State, University of Hawaii, University of North Carolina, Columbia University, a lot of them. And out of this came a lot of publications. I've never been a pretty picture taker, but I did take a couple of pictures using the 32-inch, the 0.81 meter. And, you know, here's an example. M20, the Trifid Nebula, and Messier 96. And we'll move on to the next one. I suppose here I should continue a little bit. I was the only private institution to get a $500,000 grant for deep NEO follow-up and second opposition recovery using that 0.4 meter Newtonian telescope. We employed Monte Carlo simulations to locate NEOs on their second opposition, down to magnitude 22. Unfortunately, I had to use personal funds to buy the 0.4 f3.7 Newtonian. But when not doing NEO and asteroid work, I searched for comets. And I discovered 12, many NEOs and many main belt asteroids. I've named asteroids after many famous people, including the author Kurt Vonnegut and some other people I've always respected and loved. By the way, my webpage says Michael Florian. My real name is Michael Schwartz, and I'm just honoring someone that died many years ago by using his middle name. Okay, let's go into the history of the telescope. As you can see, lenses have been played with for a long time. Ancient Egypt and Mesopotamia. Finally, after 2,000 years, discoveries in fields of science enabled engineers and inventors to start testing modern optics. Around 700 BC, Egyptians and Mesopotamians started polishing crystals, often quartz, in an attempt to replicate optical abilities they noticed that could be made in water. In 1284, this Salvino Diamante created the first wearable eyeglasses, which I am wearing now myself, except then they were made out of glass. Before the second decade was finished, Italian engineers and inventors in Venice established the first eyeglass guild and started exploring new scientific fields with full force. Even the great Johannes Kepler of the Kepler laws wrote about optics in the early 17th century. Other discoveries were by René Descartes, Robert Hooke, Christian Huygens, and of course, Isaac Newton in his book, Optics. I wish I had time to go into how important people like René Descartes were. He was a great philosopher. He established the Cartesian plane. And Robert Hooke, he's famous for his laws about springs. Huygens, you mostly see him on eyepieces. And of course, Isaac Newton, we'll talk about him later. Okay, the first telescope. Hans Lippershey was a German-Dutch spectacle maker. He's commonly associated with the invention of the telescope because he tried to get a patent for it. It's not clear whether or not he was the first one to build a telescope. And there's the man himself. I sure am glad I don't have to wear one of those collars. It must have been incredibly uncomfortable. Now the great Galileo Galilei. In the spring of 1609, he heard about this, and he quickly figured out the secret of the invention and made the 3-power telescope. Others have done the same, but Galileo learned to grind lenses. Now, those of you amateur astronomers who have ever ground a mirror, you have no idea how difficult it is to grind a lens. It takes incredible care and a lot of experimentation. In August of that year, he presented an 8-power instrument to the Venetian State Senate, and he was rewarded with life tenure and a doubling of his salary. He was now one of the highest paid professionals in the university. In the fall of 1609, Galileo began observing the heavens with a 20-power instrument. Those of you who have used telescopes should know that 20 power is not very much. Okay, so here's an overview of what Galileo did. He saw the moon phases through the telescope, saw the moon was not smooth and that it was rough and uneven. He discovered the 4 Galilean moons. He also showed that in looking at the Milky Way, that there were many more stars visible. He quickly produced a little book, The Starry Messenger, and he dedicated the book to Tasso de' Medici. Any of you who know anything about the history of Florence knows that the de' Medicis hold the pocketbooks. They were bankers. And anything you dedicated to these people was going to work out very well for you. And here we see his first observations of sunspots. And here is his drawing of Jupiter and the 4 Galilean moons. Unfortunately, the church didn't like it. On June 22nd, 1633, the Roman Inquisition under Pope Urban VIII forced Galileo to recant his views. See what happened once Galileo saw that the moons were going around Jupiter, he naturally made the assumption that Copernicus was right and that the Ptolemaic system with the Earth at the center of the solar system was simply not going to work. If he could see 4 moons going around Jupiter, he could see the Earth moving around the sun. Unfortunately, he was verbal with this, and he was brought under the Roman Inquisition, as I said, and some people say that after he recanted and said that I was wrong, that he looked at the floor and said, yet it still moves. Okay, let's talk about the age of refractors. Refractors, of course, are telescopes that have lenses. You can see by this picture here, look how long this refractor is. The reason for this is the kind of lens they used. And it causes what's called chromatic aberration. If you imagine that this is a prism and it acts like a prism, if you only use one lens, it's going to give you many colors. So they tried to avoid this by making incredibly long telescopes, which made very, very thin lenses and very, very high powers. But as you can see, these things were subject to being flexed. Controlling them was impossible. Something had to be done. And this is what was done. It's called the achromatic doublet. They took the standard lens, added another one, and this got rid of the chromatic aberration, and at the focal point, you see all the colors come together. This is the last attempt at a large refractor. This is Yerkes in Wisconsin, USA, and it was dedicated in 1897. Really what they found out here is when they make a lens this big, it starts to bend under its own weight. So this was really the end of the age of refractors. Obviously, the reflecting telescope, as we see today, was the future. And that brings in the great Sir Isaac Newton. I went to Cambridge, and I saw where he lived. And any graduate student at Cambridge could live there. And I think if I was a graduate student at Cambridge, it would have been very creepy to be in the same room where the great Isaac Newton did his work. But let's not talk about Newtonian mechanics at this point. Let's talk about the reflecting telescope. This was a piece of genius. Nobody thought that if you put a second mirror in there and looked through the side, that you could see anything. They thought this would be in the way. But it turns out this is totally out of focus, and all modern reflecting telescopes show the same characteristic. This is a picture of it. I actually had a model of this once, and you focused it by moving the primary. This is the primary mirror. Okay, Newton's first telescope had a diameter of 1.3 inches and a focal ratio of f5. If you don't understand that, don't worry about it. He eventually brought the telescope to 38 power, which he presented to the Royal Society of England in December of 1672. Now, a little bit about Isaac Newton. He was a strange man. Yes, of course, there's Newtonian mechanics. He had to leave London and go into the countryside to avoid the plague, which is much like the current pandemic, I'm afraid to say. And he worked on all kinds of ideas, but he was a strange man. After his tenure, and after his creation of Newtonian mechanics, and by the way, Edmund Halley was the only person who could approach him. He was supposedly he could be very annoyed very easily. And most likely he was gay too. Later on in life, he headed the Royal Mint. And then after that, he became involved in alchemy and wrote endless pieces about alchemy and basically religious garbage. But I could do a whole presentation on Isaac Newton. Let's talk about the mirrors. The magic word here is speculum. Okay, speculum is a combination of tin and copper, which is essentially bronze. And they didn't reflect very well. They had to be refigured all the time. And other people, like in 762, Michael, and I can't even pronounce this, the primary mirror was tilted at 4 degrees, so the image could be seen in an eyepiece mounted in the front of the telescope without the observer's head blocking the light. Now I go to the Herschels. They, of course, were in England. I was in South Africa, and they did work down there. Unfortunately, I didn't have time to pull up the pictures. But you can see this monster. It's a 49-inch, 40-foot telescope. By the way, I've heard William Herschel's music. He was a composer, and it's awful. In 1783, he completed a reflector of approximately 18 inches. 1789, a mirror of 49 inches, 120 centimeters, and a focal length of 40 feet. To cut down on the light loss and poor reflectivity of speculum, he eliminated the small diagonal from his design and tilted his primary so he could view the formed image direct. This is called a Herschelian telescope. And this telescope was the world's largest telescope for over 50 years. Now take a look at that. Can you imagine the number of people it took to operate that, to lift it? And I'm giving a shout out for his sister, Caroline. There are many, many women in astronomy who have never been recognized. They've been behind the scenes. And I wanted to include Carolyn Herschel in there, his sister, to support women astronomers. Finally, in 1845, William Parsons, the third Lord of Rosse, built his 72-inch Newtonian reflector called the Leviathan. For those who don't know what a Leviathan is, it's a whale. And here he discovered he was the first one to see the spiral form of galaxies. There's a little subnote. I once looked through a 32-inch telescope and saw the spiral structure of M51, which is the Whirlpool Nebula, but there were better mirrors and optics. All of these large reflectors suffered from poor reflectivity and fast tarnishing. They had more than one mirror per telescope, and they were frequently moved and repolished. This was time-consuming, and they had to be reconfigured to the correct shape. Now, if any of you are amateur astronomers out there, you probably made a mirror. And you can imagine what it was like to take the mirror out of this monster. Now, here we get to the more modern telescopes. This is a 100-inch Hooker telescope in California. Its dedication was 1917. I've been in this observatory, and it is incredible. There were spectrographs and logbooks lying around with names like Hubble and Humason, Harlow Shapley, and I looked at the bottom of the primary, and it was actually made out of glass from French bottles. At this point, Americans did not know how to make primary mirrors, and I saw so many bubbles in this thing. I don't know how they got to the surface without having bubbles all over the place. But this scope made some very important discoveries. Then we get to the great 200-inch at Palomar. I've also visited this telescope. And what was different about this is they finally had Pyrex. Now, I'm old enough to remember when my mother got Pyrex. And Pyrex has a low expansion. In other words, as the temperature changes, Pyrex versus regular glass will expand less. And that's what you want in a telescope. I wish I could discuss George Emery Hale and everything else that went with this, but time's not going to allow. So we're going to switch to another PowerPoint here. And we're going to talk about Webb versus Hubble. Actually, I see it's 10:25. Anyone want to get a glass of wine, take a bathroom break, have more coffee like I'm having right here? By the way, I'm in Santa Fe. This is in New Mexico. It's right next to Arizona and Texas. So I'll see you in about 5 minutes. Everyone, enjoy.
I hope you are enjoying this live. And for us, uh, for, for more live and artistical news. So enjoy your lesson, this beautiful lesson, and see you at the end, in the end.
Okay. One thing I should mention is I'm 72 years old, and this has given me the chance to see the entire solar system and the entire universe unfold. I actually saw a Sputnik. I saw Echo, which is the first, it was a large aluminized balloon that was used for communications. I saw Ranger hit the moon. I saw Pioneers, the Pioneer spacecraft unfold the outer system. I've seen Pluto, finally, through the New Horizons probe. And I've even gotten involved with, it's called Kuiper Belt objects, by working with Mike Brown, who's at Caltech. And I verified Sedna, which was the first Kuiper Belt object. It's a little complicated to talk about what the Kuiper Belt is, but it's essentially beyond Pluto, and it contains a lot of different bodies, and especially comets. A nearby star passing by, or interaction with another Kuiper Belt object is really what's responsible for comets falling in. Okay, let's talk about Webb and Hubble and who they were. This is James Webb. Now, telescopes are usually named after astronomers, but James Webb was someone very special. Here's a short biography. He joined NASA in 1968. And He was in a history project. Let's put it this way. He was an administrator of the best kind and is responsible for a lot of what NASA has done. Let's talk about Edwin Hubble, 1889 to 1953. And obviously, his big thing was he used what's called Cepheid variables, and he determined basically what's called the Hubble constant, which means the farther away you look, let's put it this way, the Hubble constant is essential in understanding the expansion of the universe. There he is himself, looking at one of his pictures of galaxies. I should also mention that I saw the Schmidt telescope. Schmidt telescopes are a very rare breed in that they are essentially cameras. And this one is still in use by my friend Mike Brown, looking for other objects. Notice that Edwin here is smoking his pipe. You should never smoke anything around optics, but I think he thought he looked cool. Now, once again, this is the Hooker telescope, and I've already described my experiences there. And he worked with the Hooker, as well as many other famous astronomers, to begin to open up the universe. Okay, let's talk about infrared astronomy. What's most important here is it started early in the 1830s, and William Herschel, the great William Herschel, discovered that there was such a thing as IR, and that the sun and the moon shone in IR light. And since we don't have a lot of time, I'm going to move on. Now, before the Webb telescope, there was the Spitzer telescope, which is a kind of mini Webb. It did exactly the same thing. Notice that the primary mirror here is segmented. All modern telescopes have primary mirrors that are made up of small secondary mirrors, and you can see them right here. This is a sun shield. Notice that this is gold. Gold is the best material for reflecting infrared light. The sun shield has to keep it shielded from the sun, because if it warms up, IR observations, infrared observations are literally impossible. Let's take a look at a few telescopes here. This one's in construction, the extremely large telescope. 30-meter telescope is in constructions. These are telescopes I visited: Mount Palomar, Mount Wilson. I went to the big island of Hawaii and saw both Keck telescopes. And by the way, their interferometry is working now, which essentially doubles the size. Now, the Keck telescope is way up on Mauna Kea at a very high altitude, and we had to stop in order to adjust to the altitude. And I spoke to people who work up there, and my perception was really affected by the altitude. First time I saw the Keck telescope, I thought, that's not so big. I've been to South Africa, and I've seen what's called the SALT telescope, South African Large Telescope. It's a very unusual telescope in that the secondary moves, but the primary does not, except for rotating. And I've seen the Large Binocular Telescope. This was the first attempt at a multiple mirror telescope, and that was right near my home, my previous home in Arizona. I don't think we need to go through the Hooker telescope again. There's a picture of that primary. See all that French wine bottle glass? I don't know how they did it, but they did it. Okay, we've already seen that. Now, here's a Spitzer image of M81, Messier 81. You can see it's quite different from an ordinary optical telescope. What infrared picks up is essentially heat. When you go out in the sun and you feel warmth, that is infrared radiation. So what we're looking at in the infrared is something we've never seen before. What do galaxies look like? Well, they look very different when they're taken, say, through the Hubble optical telescopes. Now, this is not as intimidating as it seems. This is the infrared spectrum. And if you notice in this yellow area here, we have oxygen, we have water. This is the reason why we cannot have ground-based infrared telescopes. The oxygen and the water in our atmosphere gets rid of most of the infrared. Although if it obviously does not filter out ultraviolet for any of you who have ever gotten a nasty sunburn. Okay, this is a simpler look. This is the electromagnetic spectrum. At high energy are gamma rays, X-rays, and ultraviolet. And all these gamma ray telescopes, X-rays, and ultraviolet are best observed from space. Of course, ultraviolet is what gives you that sunburn, so some of it really hits the ground. This is observable light. And here we have most of the infrared spectrum absorbed by the atmospheric gases. Once again, that's oxygen and water. Then we move over to the radio telescopes. And it turns out that the long-wave radio telescopes are also blocked by our atmosphere. Okay, let's talk about Lagrangian points. Lagrange was an incredible mathematician who took Newtonian mechanics to the maximum. And what he figured out was there are stable points around every orbiting body around the sun. This is Lagrangian point 4, Lagrangian point 5, and Lagrangian point 2. This is where the Webb telescope was placed. It's a stable area, so they have to use minimal thrusters to keep it in place. Notice this little circle here. At first, I had trouble figuring this out, but what it is you need a little circle, and it's rather complex to, because you move in and out of the Earth's shadow, and in order to protect it from the sun with the sun shield, it has to have a little orbit. And here's a closer look at it. Webb will follow the Earth around the sun, orbiting around the point called Lagrangian 2. And it orbits once every 160 days. Okay, let's talk about the latest and the greatest in who's going to discover more near-Earth asteroids or potentially hazardous asteroids. And we'll find out that NEOWISE, which is going to go up within the next few years, is going to be the main telescope for seeing new near-Earth asteroids. It will also have permanent cooling and its own sun shield. And it's designed by a very wonderful woman who I wish I had met. Her name is Amy Mainzer. She's a good friend of my friend Tim Spar. And when I was at when I was at Arizona, she was at the University of Arizona. You can see she was in a Star Trek episode. I'm definitely a Trekkie. And she has so much public exposure that she's really withdrawn from public life, and it's almost impossible to see her. Now, if you haven't seen this movie, see it. Don't Look Up. Leo DiCaprio, who, by the way, is a great supporter of environmental causes. Amy and my friend Tim Spar were consultants for the movie of Don't Look Up. Don't Look Up is essentially what happens when an asteroid is coming at the Earth. And if you haven't seen it, it is a must. The Beautiful Genius. You can see why Amy pulled away from public life. People were saying she's a lesbian. People were saying all kinds of things about her. They can't believe that a beautiful woman can be a genius. And she is a genius. I showed this before to show the relative sizes of telescopes. This was the liftoff of Webb. This is the top of Webb. Here, of course, are the segmented mirrors. This is the secondary. Light is collected here, hits this mirror, goes through this hole, and all the instruments are behind it, much like my telescope. This, again, is the sun shield. This is the bottom. Once again, the sun shield is necessary because any heat the cameras need to be kept extremely cold. They need the cold of space. And the sun shield is absolutely necessary to keep this cold. I've dealt with a lot of filter wheels in my life, but this is the most complicated one I've ever seen. These are Webb filters, and these allow them, essentially a filter allows a narrow range of the wavelengths of light, so they can look at all kinds of things. One thing about the Webb, astronomers have been complaining that there's so much data that they can't process it. It is just pouring data out so fast. And of course, getting time on the Webb is virtually impossible and is only given to the best scientists. What are they doing? Black holes? The endless search for dark matter and energy. Anyone who can explain dark matter and energy has an immediate Nobel Prize. They're going to calibrate the Hubble constant. But most important to me is exoplanets. These are planets going around other stars. I have observed them with my large telescopes, and they fascinate me. And the reason they fascinate me is because it's clear, at least to me, there is no life in our solar system. There was life on Mars, but it's long gone. And humans are very interested in finding out that we're not alone because it's frightening. So we have to look to these other planets. And here I'm talking again about search for life elsewhere. The Perseverance rover may find fossilized microorganisms. It will be interesting, but it's extinct. Believe it or not, the Chinese are doing the same, and surprisingly, the United Arab Emirates. They're all on Mars right now. This is what really interests me, the IR spectrum of chlorophyll. If Webb can ever take the time to look at the IR spectrum of chlorophyll, obviously chlorophyll is what's needed for plants. Once you have plants, and if you know anything about the evolution of the Earth, the plants came first because they oxygenated the atmosphere. Without the plants, we wouldn't be here. They breathe in carbon dioxide and they exhale oxygen. So once the Webb finds chlorophyll, we know we have found life on another planet. These are various details about Webb. And essentially, it's a 5-year science mission. And hopefully it'll operate for 10 years with enough fuel to maintain that halo orbit for at least 10 years including. Remember that halo orbit was to keep it in the moon's shadow so the sun couldn't hit it. This is a little bit about American Webb madness. When Webb first came out, women could buy earrings, people could buy things around their neck. It was really celebrated over here. I don't own any Webb jewelry, but a lot of people do. Now let's talk a little bit about near-Earth objects. They come in various kinds. They have what's called potentially hazardous objects, PHOs. And these are all asteroids, and a small fraction are comets. There's over 27,000 known near asteroids. And recently, NASA sent up a probe called DART to see if you could push an asteroid out of its path. It was successful, but it moved the orbit just a little bit. And let's talk about how likely is it that the Earth is going to be hit by a NEO? I think it's very unlikely. The last one of any impact was 65 million years ago, and this was the one that killed the dinosaurs. Except for the birds. They are class Dinosauria, but obviously, when the Earth was almost destroyed by this, they could fly to places. And so next time you say a bird, say, hello, little dinosaur. I think the greatest risk comes from a solar storm. In 1851, there was something called the Carrington event. And this is when a solar storm hit the atmosphere so hard that back then they only had telegraph, but all the telegraphs stopped working. Telegraph operators were electrocuted. And if we see another solar storm on this level, it's going to destroy every computer on the planet. So a lot of people disagree with me on this, but I think monitoring the sun is equally as important as monitoring asteroids that may hit the Earth. We always see this in the news. This one's coming close, this one's coming this one's coming that. Generally speaking, they come 2 or 3 lunar distances. And I think the probability of an impact is probably going to take another 65 million years, if at all. Here I talked about potentially hazardous asteroids. This is AU stands for astronomical unit. That's the distance from the Earth to the sun, about 7.5 million kilometers to the Earth, and 100 meters across. They would have devastating consequences if they were to impact the Earth. Now, these devastating consequences, there are city killers, there are country killers, and there are planet killers. And the likelihood of a city killer is actually not that small. But since we live on a water planet that's 3/4 water, it's going to fall into the ocean. This could create tsunamis and a lot of problems, but it certainly wouldn't be the end of civilization and the end of us. Okay, I finished with 7 minutes to spare. I'm going to give you my email address. Now, I don't have a lot of time to answer questions. Oh, one thing I want to talk about is NASA. How difficult is it to get a NASA grant? It's virtually impossible. I was the first private facility to ever get a NASA grant. And when you apply for a NASA grant, you have to use their font. There are endless publications about exactly how to apply for a NASA grant. And one thing that I thought is very unfair is NASA grants can only be given to Americans, and you can only hire Americans. But you're perfectly able to buy a telescope from China or Austria or anywhere else. I thought this was very unfair. But if you're ever thinking of getting a NASA grant, get ready to do a lot of work. And I did. Now, I was offered another 3 years to continue my work, but I told NASA no, because I had done another proposal that added a 3rd telescope, and it would have been a fantastic system, but they said no, and I said goodbye. I actually sent my friend Tim Spar out to me in Arizona to try to talk me out of it. Okay, I see we're at 10:55. Let me give you my email address. Now, I'm not going to have a lot of time to answer emails, but I'll do the best I can. It's Tanagra, T as in Tom, E as in Edward, N as in Nancy, A as in Alpha, G as in George, R as in Roger, A as in Alpha. Is that right? Tanagra, Tenagra, at proton, just like the particle, mail, mail.com. Now, once again, I want to thank Gerd. He has done a tremendous job in this. And I want to emphasize one other thing. And that is the earthquake.
Thank you, Michael. Thank you.
One more thing, Gerd.
Thank you very much. A very interesting I hope to see you again.
Everybody, Gerd has a certain neurological disease, and he's very difficult to understand. But he has done a tremendous amount of work here, and especially with his handicap.
Yes.
And I want to mention one more. I want to mention one more thing. There are people suffering in Syria and Turkey because of this horrible earthquake. A couple of euros will take care of a family. And regardless of politics and what you think of these countries, these are people. And they're having a very difficult time. So I thank all of you for listening. Tassos, I hope you were in on this and could understand a little more. And I'm going to sign off and say thank you so much to Gerd. Unbelievable man. Just unbelievable.
Thank you. Thank you.
So